There we go.
Woo! Awesome.
Save the day!
Thank you, Doug. I mean, Paul. Who all went to Duncan's, I'm sorry, the presentation before over in the other track? Duncan Manuts. That was good. Yeah, I felt kind of personally affronted at that. How y'all doing today? Good con so far? First run? Rockin', right? Thank you, Chris. So my name is Atlas. I'm going to cut right to it. I've got like 40 slides in 50 minutes, and my normal time is like 2 minutes a slide, so we are going to bust through a bit. Who here read the brochure before they came to the talk? Half of you are going to be half disappointed, but I hope to make it up. The original talk that I prepared for this gave some people that are very close to me some trouble, and I had to change it. So if you were coming here to learn the latest, greatest ROP techniques to sploit on DEF CON challenges, I'm sorry. We've taken a different exploitation route. It's really awesome, and it includes something I like to call transword beaming. But I think it'll be good, but I just wanted to warn you, if you came here for just the ROP stuff, you might want to leave. I threw together a presentation that I could not make under an hour and a half. So, I've left the meat in the slides. I'm going to skip the first slides because they're really not relevant to the actual overall presentation, but they're good informational. But I wanted to leave them in there for you. They talk about ASLR, NX, DEP, other randomization stuff, a little bit about how to tell if randomization's turned on for an L for a PE binary, Windows and Linux or Unix. And we're going to skip straight to capture the flag. Who here's been to DEF CON? All right, good. That's about 3/4 of you. Awesome. Have you heard of capture the flag at DEF CON? If you've gone to DEF CON, you've heard of capture the flag. It's like the prize event, whatever. So, this is not a talk about DEF CON. This is not a talk about capture the flag. Actually, an excellent talk on capture the flag at DEF CON and the ins and outs and how it all works, who the people are. It's going to be given by this guy right here, Jared, a couple hours. What time? 6 o'clock in this room. Awesome. Come back for that. You can catch all the backstory then. So every year, DEF CON puts on a capture the flag game. And if you played capture the flag games at all, more than one, then you understand that no two are alike, and they range from, woohoo, I can throw a tick mark in an input field to a web application, to holy crap. I think this is a Department of Defense application that I'm hacking here. So, widespread. DEF CON's actually about 3/4 of the way up the scale. They are difficult. It is binary reversing and exploiting, and a heck of a lot of fun. The only one that I found that's even harder is the one in CodeGate, where they just said, okay, fully patched, latest everything gizmo, and you guys figure out how to hack it. But capture the flag at DEF CON is really a great deal of fun. And each year, they have so many teams that they have to give a qualification round. So hundreds of teams sign up, and the qualification round consists of a weekend. We start on Friday, end on Sunday, and it's like Hacker Jeopardy, kind of, where you've got different categories of stuff, some really lame and annoying stuff, and the pinnacle of the whole event is generally Pwnage 500. So you've got things like reverse engineering, binary leakness, and some forensic stuff, and maybe some, they had some really nasty stuff this year for random crap called a grab bag. But the Pwnage is always my favorite. Basically, you always end up with some sort of a program running on some machine. You have to compromise it, take it over, get a key, or something like that. Pwnage 500 is normally the awesomest, and this year was no different. This year's challenge included a binary that you tell it to a port, and it gives basically an interactive menu. So Scroll through, it kind of looks like a database application. You can add records, delete records, update records, view records, and download records, and then you can quit. Sounds easy. Let's break it. So the first part of the pain of this challenge, because it's generally so contrived to make it that much harder for weeding out the extra individuals that they can. It's like stuff you never ever see. Like in this case, just to be nasty, the menu was randomized. And you had to go through the menu a bunch of times to be able to hack the binary. So I don't know if you can see that very well, but it's several iterations through the menuing system, adding, editing, deleting records. And you'll notice I put red circle or red squares around the upload new record in the first menu. It's number 6. It's number 1 in the second. It's number 3 in the third, and number 3 in the fourth. So you have to be able to. I mean, you start out. It's not really neat, but it costs time to write code that parses text, makes sense of it, and then does better stuff. In fact, I ended up writing the code for our team, and I got a message in some notes on somebody else's exploit. It said, "Buy Atlas and vodka," because I had made his life that much easier. A few of the details about the binary. It was an interactive text web application. It used C++ standard lib templates. Who here has programmed some C++ before? Okay. You ever use templates? Good. I'm just going to message you. Templates are really a pain in the butt to reverse. I mean, it's not really difficult. It's just kind of annoying, again. So the idea of this application is all based around creating, deleting, updating records. In the finer details, these records are created in a heap. So you do a malloc, and when you create the records, it creates two structures and an object. The object is your record. Another structure or piece of memory that gets allocated is for a hash representation of your record, and another one is a structure that points at other things, including your record. So, weeding through memory, it can be interesting. We're going to do it a little bit more in a few minutes. And we noticed that if we threw it on different Linux boxes, it behaved differently. Occasionally, when you update a record, the thing would just go away. Go boom. You hook up GDB and you get some sort of segfault. But only occasionally. So, okay. And it didn't matter, you did the same thing every time. And it'd break half the time. So we tested on Ubuntu, CentOS, and I ended up focusing on Fedora because there was a library or a constraint of the binary that asked for a very particular version of libcrypto. The only one I could find for it was Fedora. Turns out the two that we focused on the whole time are a real pain in the butt. They have full ASLR, full depth, and that causes us a lot of problems. Turns out Fedora doesn't have NX turned on, at least on the boxes that we were using. And it turns out the boxes that we're using for the challenge itself. So that sounds interesting and all, but so what? We want to break this thing, right? So they threw in a smattering of challenges to make breaking hard. The first one was a lame password protection, which clear text password stored in a binary. We kind of use strings to reinforce that. Standard lib C++ templates. There was stack heap randomization. As you're going to hear a recurring theme here, we kind of thought that it had NX, otherwise known as dep on the Windows side. We thought NX was turned on. Wasn't. And they were doing a standard server. You accept, you fork, you do a new process, and then you run. But they threw in an additional pain in the butt process where when it forked, it didn't just fork and then do its thing so that each child would just go serve a network socket. No. It forked, it executed another version, another copy of itself, handing in a parameter that allowed this new program to handle the socket request. So what? Why is that so hard? Well, because when it execs, the loader re-randomizes shit. So you can't just have one exploit where you find a peak and you can figure out where stuff's at, and then throw another one in and actually exploit. You have to take good care so that when you figure out where this randomization stuff is at, that you don't crash the binary. Because it's only like that for that child. They also threw in a random, they like dev random, or dev random. So they threw in the record creation routine. They read 4 bytes from dev random and then turn it into a number. And if that number was odd, it created one kind of object. If the number was even, it created the one it wanted. Again, just a real pain in the butt. Let's see. Oh, and there's Taroot. But I won't get into that too much. It was kind of silly. So let's focus on the VF tables right now. VF table, anybody heard of them? You've all written C++, which have you reversed it? When you create a C++ object, there is a virtual function table created for that object. Well, created for the class of the object. It isn't created in copy. And each object of that class, at specific points throughout the object, have pointers to a virtual function table. So when you said object plus plus, the runtime says there's an operator plus function that gets called on this object, so it looks in this specific place in the object in memory for the pointer to that function table. And an offset into that function table, so you get the right function pointer. And then it goes and executes that function. Little odd, I've got some diagrams in a little bit that'll make that easier. But basically, that's what a virtual VF table pointer is all about. When you create different objects, they're of different classes. They have different VF table pointers. And in the virtual function table for the object that we get, if your random bytes are even, there's an overwrite in the update function. So when you upload a new record, and then you edit it, it always clobbers something. Again, it's a bit contrived, but in most well-used applications, this would never exist. But it made it tough. So in one of the update functions writes the correct length. One writes OXF8 bytes, so really close to 256 bytes, 248 bytes. And that object is only E8 bytes from the end, so you get an entire 16 bytes into the next object, or the next memory allocation, to play with and be your bitch. You will notice that my presentations are slightly different than Duncan's. You'll probably be sworn out a few less times, but I do apologize for that. So here's a diagram of the overwrite in code. So we've taken binary code, we've reversed it by translating the machine bytes into their human-readable assembly instructions. We've done some analysis on it, and this is the stuff that gets kicked out. If I had my laser pointer, which would have been great. So I just named it dirty overwrite. Sets up, yeah, that's great. Let's tap it. Sets up some normal stuff here, and you'll notice right down here, we compare our counter against 61 iterations through a double word copy loop. Double words how big? 4 bytes. So at 61, you rock. It's not going to burn anything, right? Okay. Awesome. Oh, yes, it is. I won't leave it on too long. I don't want to burn it. Have you seen the Arctic lasers that they're selling for like? Well, no, the greens are 1,000. The blues are still like $300 for 1 watt. Anyway, no, that's not on my Christmas list. So, exactly. So basically, we come down here. I'll just kind of walk through. Oh, jump down here. Oh, compare our counter variable that we're going to track against 61. Well, it starts out at 0, so it's 0. So hey, it's so we test to see if there's anything in the result, and it's not. So we jump back to here. Oh wow, look at this. We copy into a register the dref of that register, which happens to be the source, the current source. And then we take that value and we shove it into the dref of EAX, which happens to be the current pointer to our destination. So it goes boop, 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 boop. Don't try to copy the sound effects, they are patent. And so we loop through this 61 times, or actually 62 times, which 62 times 4, 248. And after doing an overwrite, you'll notice, and you'll see this in a minute, here's the beginning of our first object, the one that we're editing. This is the VF table pointer right here. Remember that well. That looks like it could be a size variable because this is stuff that I've shoved in there. And then a whole lot of nothing until we reach down here to another copy of the VF table pointer. And another thing that looks like the size, and hey, these look like they could be identical objects. Very, very close. So after updating the first one, blah, 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 we throw in a whole bunch of A's, blah, 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 blah. And we overwrite. Oh my gosh, look at that size. That's a little bit bigger, don't you think? Well, that's because our overwrite actually copied data. And we overwrote up to this point. Actually, right there. So we've shoved in. Well, wait a minute though. The VF table pointer didn't change. That's because I didn't want it to. I actually overwrote it with the exact same bytes that form that pointer. More on that in just a moment. So, how did we handle these challenges? Real quick. Password. Lame. Blah, 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 blah. Hey, here's a string pointer that's been called against compare. That looks like it might be something of interest, don't you? Oh wow, hey, if I follow that pointer, there's the password. Try it out, sure enough. Standard C++ templates. You will notice in this dump, just a slide ago, this call, blah, blah, right here, very different from what it was original. This, this right here is the name that was put into the binary and the name that got shoved into my tool. So, turns out, std C++, the library, has in it a demangler. Pretty cool, huh? My tools typically end up in Python, so you will see Python code on the screen using C-types. Anybody use C-types in Python? You must. By the time I see you again, I want that hand to go up, all right? C-types in Python is a Pythonic way to load up compiled libraries from the operating system. So in this case, I find the library standard C++, and then I run through all the symbols through this little convert, where libs standard C++, CXA demangle is called, and it turns this into that. that is a pain in the butt enough to process if you're not really, if you haven't done a whole lot of C++ programming. This is just darn plain impossible. I spent a little too much time, more than I'd like to admit, debugging these stupid C++ things. Because, I mean, come on. It doesn't even tell you what it is, except it turns out it's a destructor for all sorts of this stuff that is just baked into standard C++ naming. We also had the fork hack and the stack heap randomization. We really can't do anything about this in an exploit, so that this will never be an exploit that you can just throw and it works. It will always be, it might work, it might not work. The job of the exploitation manicurist, if you will, is to make it work 50% of the time, not 20% of the time, because we can get around certain oddities, but we can't get around the fact that sometimes you're going to get it when the updated record is just not vulnerable. So it doesn't really help to do anything to your own system to make the exploit work better, except when you're developing the exploit. Why? Well, I want it to work every time the way that I want it to. Here's the code that actually does the exact nonsense. Up here you see the call to accept. That's a network socket accept, and it's returned what comes back as a file descriptor for that network socket. Then we call fork. This is all looking really standard for a lot of stuff. And then we build up a new command line argument list using sprintf. Then close the socket, and oh, exactly, you suck. Here's some code that actually selects our which object we're using. We have a file descriptor for d00m. We read in 4 bytes. And then right here it says, let's AND those 4 bytes with the number 1, test it, and well, if it's 0, jump down here to D78 and create this object. If it's 1, we create the object right here. This is like fodder in case you decide to throw the binary into IDA and go do it yourself. So what can we do? Well, we kind of have to brute force and just say, we're going to hit it till it works. This is not the ideal case, but hey, it works. For our testing, however, since we want the 0 in that 1's bit, do this little hack called rm d00random and linking d00random against d00. So everything that gets read out of the device d00, well, it's a 0. So we always get, every time, the object that we want. It's a win for dev. It goes fast that way. It only works for 0 though. However, if we needed the 1s, we just throw a whole bunch of 4-character stuff in there that is odd number basically. So why did I choose A? Jared, why did I choose A and not B? 4-1. Yep, hex 4-1. That means there's a 1 in the 1's place. I could have chosen 0-1. I like it. Not in 30 seconds. This looks really blurry, and it's not blurry on the slide. Is there Mr. Projector Man? No, I'm not talking about you guy in the back. The guy next to it. Can you? Is there a way that he can modify?
There's a focus button.
Well, we're in focus mode now.
And then
That got slightly worse, I think. Yes. Damn the Windows protectors.
Focus and plus and minus.
There we go. You mean it's not a binary command? Woo! My eye doctor, apparently I'm not loud enough. Wow! So as you can see, this is actually code. All right. So the random menu was kind of lame. I got this over here again. You can actually read it this time. Upload new record, upload new record. So you got upload, view, edit, delete, download, quit, and a view summary. This is actually something kind of funky, scrapes through all the records and kind of gives you a summary of what's in there. So I wrote a little code here. I won't go through it too much, but it's basically something that reads in the menu, and then something I can call in my exploit that says, you know what, I don't really care. Send a delete, whatever. So it reads in, finds the delete, parses, it goes out. Another challenge was an unknown Linux environment. We didn't know what to expect, so we just expected that it was ASLR and NX, which was a smart game than I care to admit. And it was chrooted, except it was chrooted to root. What? That was just a fear tactic. So scraping through the memory usage, we put a breakpoint execution thing on malloc and free, and we grabbed the size of our allocations and some other tidbits of information I'll show you in a minute. But just the brutish thing, this D8, this is one of the types of objects, and that FO is another type of object. These 18s and 27, 64, 4, really? That's a lot of mess. Holy crap. Well, it turns out that most of the things that are allocated, they're transient. They go away really quick. So you'll notice we turned on grabbing the address and the size, and then we hit it against free. And the 64s and the 4s dropped out, and it turns out all that was left were 3 memory allocations. The first of which is an ASCII representation. One second. Size. Yes, actually, it's an ASCII representation of this string being shoved through the MD5 function. The next one is our record. Notice this is the little endian version of our VM table pointer, and our size and some other stuff. And then the last one is a structure that points at what? Well, it turns out they were storing. Who here's heard of an RB, a red-black tree? A red-black tree is basically a binary tree that has certain algorithms wrapped around it to make searching through a red-black tree very, very fast. Now, it's not the fastest to store into, because every time you store something in a red-black tree, you refactor the red-black tree so that it's faster to search. But that's what they were doing. They used a red-black tree implementation that's pretty standard, but that's what the structure refers to. And it gets created for every object, so that every object points at something, either the root of the tree or some other object in the tree, or a couple. So again, a couple representations of the data that we are dealing with. We have our red-black tree pointers, and then a pointer to our hash string. Oh, so that hash string kind of gets tied in there through the structure. And then a pointer to our object that starts right here. The transient items happen to be your menu items and other ancillary data that gets created along the way. And a couple representations, sorry. So now what? So we know that 50% of the time, we can create a record and then overflow outside the record into something, right? So now what? Well, can we predict what's after the record? This is the heap, right? So you can, Jimmy John can create whatever he wants in the heap. Oh, you rock. Hello, I am Duncan. Duncan Manutz. I actually was going to wear Duncan's beard up here, but yeah, we decided his laptop was done.
You shaved Duncan's beard?
You. Yeah. So what can we do? So we overwrite. We have to then try to figure out how to get two objects side by side. And then we overwrite what? We overwrite a VF table pointer? Not yet. Maybe sometime soon. Do we overwrite a function pointer? Well, we haven't found any function pointers. I've shown you the data objects that are actually created and stay on the heap. But that length field, now that length field looks very interesting. So, why is the length field so interesting? Well, we have data randomization, remember? The stack and the heap, they're based at a random location for every time we hit the server. So we need to understand within, what, 12, 13 bits of randomness, depending on your implementation, where that stuff is. 12, 13 bits, that's a very large number. Your NUP sled is not going to cover that length, but if we groom our heap so that we get objects created in just the right way, we might be able to turn that length field into something. So the plan, we'll groom to open holes so that the pointery things, the things that aren't our objects, they get dropped into known locations, at least relative to the stuff that we're working with. We'll overwrite the length field just before a hole of an object, just before a hole where these pointery things are being dropped into. And we call view record, and the view record depends on that size field to see what comes after. So the grooming. No, this has no use for a comb. Moose is really, well, Moose, if talked about at GrrCON, might be helpful. But grooming is where we create objects, delete objects, and the particular pattern that we do so leaves free space in the heap that then can be reused by other things. So we create one record and then we delete it. So that leaves two little objects and one big object. Turns out the two little objects, they don't get deleted when we delete a record. So the object that we created gets deleted and its space can be reused. We then create three more records. So that 248 byte allocation, it now is taken up by two hex 18 size objects or allocations, and we end up with still a hole there as we create the next three records, back to back, all of them together. We delete the next one, leaving another hole. Then we create 7 more. So what does this do? It kind of creates something like this. These little tiny records, A representing one, B representing another, and then our record, the actual C++ object, another C++ object, another gaping hole, and then another object, or a whole bunch of objects that come after that. So as we create these objects out here, what happens to their administrative memory doohickeys? The struct and the hash string. What happens to them? They get shoved in here. And as soon as this fills up and we can no longer allocate out of this small space for the smaller objects, they start getting shoved into here. So what? So I can tickle memory and twiddle and play, right? was a great segue. Let's take you down the next path, and then I'll get into that. So when we do our overwrite, here's what memory looks like just beforehand. We've got our object, our VF table pointer, our size of the first one, and then stuff. This actually turns out to be an index of the created objects. This is the 8th one created. From here, I'm using up all your data, dude, sorry. Oh wow, it just likes to be shaped. Then we have our second object. Ignore the F9, that's just a heap administrative thing. After the override, we now have a very large size in the second object that we've created. And then, wow, these kind of look like pointery thingies. How do we know? Because they look a lot like these numbers right here. So when we call view record, we get a whole bunch of this nonsense. Parsing through there 4 bytes at a time, however. Take out the D words, and we find interesting stuff. This is from a different run. I do apologize. I've got some inconsistencies in the data that I'm showing you because it's from like 20 different runs. So this happens to be where the heap is based somewhere closer to hex 888. So we take that and we say, hey, this is the base address of where our junk is. And here's where we're going to think our VF table pointer is. And here's where we think our target record is going to be. I clean this up a little bit on a different run later. And this is what it ended up looking like. So notice, there are a lot of these that have the same first 4 hex digits, so the first 2 bytes. So we extract out a base address from that, and that tells us a lot. So now what? Well, now that we know, relatively speaking, where stuff is in memory, in the heap, why relatively speaking? Well, because we still have that randomness thing to overcome, and the different objects happen to be different sizes too. So the objects that we end up controlling and playing with may be shifted a little bit this way or that. That's all right. We'll figure it out. So this time, let's overwrite the VF table pointer. Let's just use the same 2 records, just cause. We'll access the register to trigger the VF table pointer, so we'll do something to that record. We'll delete it, we'll edit it, we'll update it, or view summary actually would call something, so that the program itself will then call some offset dereference into our VF table. You with me so far? If not, it'll still get a little clearer in a minute. We then create a fake VF table that we point into. That offset into our own fake VF table will then point into our shellcode. You with me? You want this to happen? You're kind of doubting. So here, first part. Overwrite the VF table pointer. Oh, hey, wow, I'm kind of, this is a, call it, spoiler. So right here is our VF table pointer. Well, what the fuck is all this? I mean, this looks very similar. Okay, well, whoa, wait a minute here. This right here, VF table pointer, when it gets called, or when we call something to do with the records that we create, this thing's going to be dereferenced, meaning the 2574, which is this location right here, will be used as the base for a VF table pointer, which is just an array of function pointers. I'm sorry, a VF table, which is an array of function pointers, and then we'll have some offset into that array of VF, a virtual function table. Sorry, function pointers, one or the other. So here's how the exploit's going to work. We've chosen to trigger this exploit by using the edit record function. Should have chosen something else. It says dref that df table pointer basically shoves the VF table pointer into the EDX register, adds 12 to it. That's our offset. Remember, we said we were going to have an offset into that virtual table, the virtual function table. We then set up our stack variables and we call that offset into the virtual, that function that we pointed to. Look at it down here. In memory, here's our first object that we've put in all these numbers that look very much like these right here. We've overwritten the virtual table pointer, and wow, do you think this might be shellcode? I think it might be, especially since I wrote it on there. So our VF table pointer points back to this location. Oh, but we add 12, right? How many keywords is that? Yell it out. 3. So we say 1, 2, 3, right here. Well, what's that? 25FC, 25FC, right to our shellcode. Well, like, so, oh, wow, okay. So now what? Why all this other nonsense up here? I mean, I ended up right there. Just give it the one that we want. Well, because as the random function decides how big each allocation is, this thing slides all over like 60-some bytes in my experience. I haven't done the math, but so by creating a virtual table, every one of these, depending on this location, will end up in shellcode. So this is what I'm referring to as transwarp beaming. You guys seen the new Star Trek, right? J.J. Abrams, rocking. It's like Star Trek the way it always should have been, with Star Wars wrapped in. So you got Scotty, and he's like on this lame-ass moon or planet or something that has really scary creatures, totally kicked out of, basically at the very bottom rung of Starfleet, going, you know, I got this idea. I tried it on my boss's dog, and well, look, I ended up here. But the dude figured out how to account for like 2 different moving objects moving at warp, doing really crazy shit, and that's kind of what I think this is. Where my VF table pointer is going to move around, the virtual table is going to move around, and basically I just picked one place in memory, and I trued it up to that spot and added 4 and subtract 4 from there. And it works. But so, well, we kind of constrain on shellcode, plus I've been challenged by a friend of mine who says, you should be able to write shellcode in 5 minutes. So, I worked on it. We don't need, like, everything. We don't even need a shell, per se. What we need is we need to read in a key file and spit it out over the network socket. Very important point, don't try to do this at home if they close the socket before you take over the execution. I learned that the hard way at GrrCON Capture the Flag this year, actually. So all we really need is open key, read in data, spit data out on the socket. And if we're really nice, we exit nicely. And this is a little, it's actually not too bad. If this causes eye strain, don't sue, you may move up. But, real quick, if I don't fall off. We start our shellcode by jumping to strings, right here, and then calling string callback. What the heck does that do? What happens when you do a call? It shoves the next instruction, it shoves that on the stack. That can be very helpful. So we pop off that location, which is pointing right at key. Pop that off, shove it into a register, and let's store it just in case we need it. We push on some arguments for our call to the open function, and then there's no call here. What? Well, we set up registers, and then we do a syscall. You guys familiar with a syscall? It's the way that libc talks to the Linux kernel or to any other kernel that uses the C library. Windows is very similar, except that you want to talk about transwarp beaming. They change their index numbers like every release of the operating system. So we do an interrupt 80. Anybody heard of that? Interrupt 128, hex 80. That triggers and says, hey Linux, I've been trying to get your attention. This is something that you need to do in kernel mode. It jumps in, reads in the sysopen, says, oh yeah, okay, I can open that. Oh, the file name's right here. Okay, I can open the key file. And EAX is returned the file descriptor to point at that key file. We then read it in by setting up in a very similar fashion where we're going to write. So we'll just stick in the same address as the location for the data because we don't really need it anymore. And we'll read in up to 255 bytes. The typical key file is like 30 or ish. And then we read it in the same fashion. Hey, we push sysread, pop it into EAX. This is just a cheap way to make sysread show up in the EAX register. We call the kernel. Kernel does that read for us. Again, this is actually what libc does for you. And we store the number of bytes in EDI. And then, hey, we set up a call to write to the socket. And we use the number 4 as our file descriptor. It turns out, when you fork right after an accept, your file descriptor is always going to be the same. The file descriptor that points to the socket, it's always going to be the same because every new connection in there forks. If that file descriptor happens to be equal to 4 in the first child, then it's going to be there for every other child because there's nothing in between there to open new files in between. So I suppose Linux could like randomize that. I would not like that. So, real quick, lessons. Know your tools and know that you know your tools and know why you know your tools. Understand GDB, understand shellcode, understand things that you're putting together, and use tools that you vetted to inspect exactly what the tools that you're writing are doing. Transwarp beaming. That's a cool lesson. Shell coding. Yeah, if you're trying to save space, don't just try to push a word instead of a D word for a number. Save 1 byte and it doesn't actually work. And it turns out that the call to read doesn't like a maximum read size of like 2 billion. Well, take clues to the platform that you're targeting and at least try to trust them. And if you're doing anything for CTF, try shellcode first. Because you might do a ROP, but it might be a waste of time. That's all. Thank you very much. The creator, Tool, Bug, Spring Rate, Viva, Soto.